We said that when we're solving a system of equations by graphing, we're looking to see where the lines intersect. Where the lines cross, where they intersect is going to be my solution. But what about when things get weird? Because we've looked at examples where the lines cross just once, like we'd expect, but it's possible that lines cross more than once, or even not at all. So let's take a look at what's going to happen in those situations. So I'm actually going to start with the second example first, because it's a little bit easier to do. And so I want to solve this by graphing, so I'm going to rearrange both equations to get y by itself. So that would involve subtracting 2x, so y equals negative 2x plus 4 for my top equation, and then y equals negative 2x plus 1 for my second equation. Now actually, without even graphing this one, if I know what's going on, I can see something interesting right here. Both of the lines have the same exact slope, which means the two lines are going to be parallel to each other. So I don't want to graph this one, but if I imagined it, I mean, you guys know what parallel lines look like. So these are not the actual equations, those are just a freehand sketch I made. My two lines are parallel to each other, meaning if I asked you where they intersect, hopefully right away you'd tell me, well, they don't intersect. And because intersections mean solutions, this problem, because the lines are parallel, actually has no solutions. The graphs never cross at all. So there is no solution to this system. In my first example, again, if I were to solve for y, I could do that just kind of for time, because we're talking about what happens when things get weird. What I want you to look at is look for a pattern between these two equations, to go from the top number to the bottom number. And hopefully what you're realizing is that every single time, all you're doing is multiplying the number by 2 to get to the other equation. What that's going to mean for you if you did happen to solve for y, and you can go ahead if you don't believe me and actually solve for y and see this, it turns out that you're going to get the same exact equation for each of these when you simplify it, or not simplify, sorry, when you solve for y. They're the same exact equation, meaning when you graph it, if one of your lines looks like that, your other line, since it's the same exact equation, is going to be right there at the same spot, meaning they're the same line. If I were to ask you where two lines intersect each other, if they're right on top of each other, hopefully right away you tell me it's everywhere. And in fact, this is a system where you'll have an infinite number of solutions. Any point you pick on that line will work in both equations. So here's our two examples of the weird problems where we don't get just one intersection point. We either get infinite solutions if the lines happen to be the same line, or no solutions if the lines happen to be parallel because there's no intersection point. So we have a couple of vocabulary words associated with that. So let's go ahead and just make note of that. We'll take a look at one more example to finish this up. So the words consistent and inconsistent. Consistent just means that the problem does have solutions, or it has solutions. Whether it's one solution or infinite solutions, we don't know yet, but it has solutions for sure. Inconsistent, on the other hand, means the problem has no solution. So that second problem, well, on the right side problem we looked at last time, was an example of an inconsistent system. The lines were parallel and had no solutions. If we say that something is consistent, we have to go a little bit further and say whether it's independent or dependent. Our normal lines that cross once are consistent because they have one solution, but we also say they're also independent because they have one solution. The dependent lines, or I'm sorry, the lines that were the same, and if you're looking for the second line in the picture, remember the second line is right on top of it. So we'd say that in that case, the dependent problems have an infinite number of solutions. So in that example on the left on the previous screen, we looked at an example of a consistent but dependent solution because there was an infinite number of them. Okay, so there's our vocabulary associated with this. I'm really more concerned about how many solutions it has, but let's go ahead and take a look at what happens if we try to do elimination or substitution. We saw what happened graphically to get our weird answers, but watch what happens if we try elimination or substitution. I'm going to do elimination just because I prefer that, but a similar thing is going to happen if you were to try this with elimination, or with substitution, sorry. So what I want to do is I want to add my two equations together. And I don't have any opposites right now, so remember our trick was to multiply by a number that would get you opposites. So I'm looking at the x and looking at the 3x and knowing that if I multiply by negative 3, I should get the x's eliminated. So I'm going to multiply everything in the top equation by negative 3. So I get negative 3x plus 6y equals negative 12. And watch what interesting thing happens this time. My x's are eliminated like I had planned, but what I didn't plan for was the y's also to be eliminated. 6y and negative 6y also get eliminated, so what's left over here is really just 0. There's nothing left. Anytime both variables drop out, you should make a note that something strange is happening. If I add the other sides together, I get a solution of -4. And as I can see, this is weird, and that's actually a false statement. 0 does not equal -4. What this means is we don't have a solution. We have an inconsistent problem. So if you're doing elimination and this happens, where you get a false statement, both your variables have dropped out, what we'd say is that there is no solution. And if you remember back what that looks like graphically, no solution means no intersection points. So those lines, in fact, if you graph them, would end up being parallel lines. And then if I were to classify this, our vocabulary word associated with this is inconsistent. We say that this is an inconsistent system. It's parallel lines, they have no solution. Let's take a look at the second example. You can probably guess what's going to happen this time. Again, I'm going to stick with elimination because I like that, but a similar thing will happen if you do substitution. So I'm going to look at eliminating the x's again because I can see that an easy way to do that would be to multiply the top equation by 2. That would get me opposites. So I'm going to have 8x minus 10y, or minus 20y, and then equals 16. So again, like I had planned on, the x's dropped out, so they were eliminated, but also the y's drop out, so I'm left with nothing on the left-hand side of this equation. And actually also, look at that, everything is canceled out this time. -16 and positive 16 also adds up to 0. So because everything got eliminated, that should tell me that something interesting, is happening. So this time though, I have a true statement, 0 does equal 0. So what that means is it's not that my solution is 0, 0. In fact, what this means is I have an infinite number of solutions. Both variables are gone, but I'm left with a true statement. So I have infinite solutions in this case, meaning if you were to graph this, the two lines would be the same line, they'd be right on top of each other, which if we wanted to classify this, we called this the consistent and dependent solution, meaning consistent, we did have solutions, but dependent because they were exactly the same lines, we have an infinite number of solutions.